In this video, we're going to explore the difference between physical and chemical properties. As mentioned before, mixtures can quite often be separated by taking advantage of differences in their physical properties. The example we used earlier was if we have mixtures that have different states of matter. If we have a sample that has solids and liquids in it, we can likely separate that sample by using simple filtration. If we have a mixture of sugar and iron filings, those iron filings are going to be magnetic, and so we will be able to separate them by using a magnet. Boiling point is another physical property we can use in order to separate things by a process called distillation. If you have a sample of salt water and boil it, as long as you are able to collect the water off in a different location, you will separate the water from their salt because they have very different boiling points. We will usually define physical properties as characteristics that can be evaluated or investigated without actually changing the composition of the material. In other words, if we're trying to find the melting point of gold, we can simply heat it up until it melts and find the temperature at which it melts at. If we let it cool back down, it will become a solid again, and it's still gold. Likewise with water. If we want to know what temperature water boils at, we can boil it, find that temperature, let it cool back down, it will become a liquid again, and it's still H2O. It hasn't actually changed its composition. We can find the density of any material by simply finding the mass and the volume of a sample of that material. Doing so does not change the composition, does not change the chemical formula of the compound that we're investigating. Physical properties can be broken down into two different types, either extensive or intensive properties. An extensive property depends on the amount of the substance. Mass is certainly a physical property. However, the mass of a substance will change depending on how much of that substance we have. If we have more of something, it will have a larger mass. Intensive properties, however, do not change no matter how much of that substance we have. If we have a thimbleful of water, its density at room temperature will be approximately 1 gram per milliliter. If we have a tub full of water at room temperature, its density is still 1 gram per milliliter. Likewise, the boiling point of water. The boiling point of water is 100 degrees Celsius at atmospheric pressure. If we have that thimbleful of water again, it will boil at 100 degrees C. An entire tub full of water will also boil at 100 degrees C. The actual temperature at which water will boil does not change no matter how much of it we have. That makes it an intensive property. What will be different is the amount of heat, the amount of energy we have to apply in order to get it to that temperature. We will be discussing energy later on in the course. Physical properties are a function of something we call intermolecular forces. Intermolecular forces are the forces or interactions that exist which hold the molecules of a substance to each other. Methane, natural gas, only exhibits what we call London forces, which are very weak intermolecular forces. On the other hand, water exhibits what we call hydrogen bonding, which is a very strong intermolecular force. What this means is that it's much easier to separate the molecules of methane from each other, so it requires less energy to do so. As a result, methane is a gas at room temperature. It is harder to separate the molecules of water. It requires more energy. So water is a liquid at 25 degrees Celsius. Physical properties are affected by the temperature. Remember that temperature is just a measure of the molecular motion. As we can see here, for instance, the density of water changes at different temperatures. At a temperature of 0 degrees C, we have a density of 0.917. If we have still a temperature of 0 degrees C, but now in the liquid phase as opposed to solid, our density increases. If we go all the way up to 100 degrees C, we have a density of about 0.96. This might seem like small differences, however, it's important to note that it is a difference. Different temperatures of water will have different densities. Investigating chemical properties requires a change in the actual composition of the material. In other words, in order to investigate chemical properties, we need to see how one substance reacts with another one. In doing so, that will change the composition of whatever we are looking at. The chemical reaction tells us how the change occurs. An example of this is that one of the chemical properties of wood is its ability to burn, known as combustion. So if we have wood and react it together with oxygen, we produce carbon dioxide, water, and heat. The reactants are very different from the products. So in order to investigate this chemical property, this ability of wood to burn, we've had to change its composition. We've had to change it into something else. When we're investigating chemical properties, what we're really investigating are chemical changes. In a chemical change, the actual composition of the substances will change. We create something new. For example, if we react together oxygen gas and hydrogen gas, we can form H2O. And so one of the chemical properties of oxygen is its ability to react with hydrogen. Likewise, one of the chemical properties of hydrogen is its ability to react with oxygen. When we're investigating those chemical properties, we are sending those substances through a chemical change to make water. Chemical properties of elements and compounds are related to something we call periodic trends and to molecular structure, which are two things we will be studying in detail later in the course. Physical changes, however, do not entail any change in the chemical composition. If we have solid iron and we melt that in a blast furnace, we haven't actually changed its chemical composition. It's still iron. Likewise, if we melt an ice cube, it's still H2O, it's still water, it has not changed. And we can easily get the substance back simply by cooling it down in these cases. And so physical changes do not change our chemical composition. In other words, they do not make anything new. We still have the same substance. Whereas chemical changes do involve a change in chemical composition, changing the composition or structure. They result in something new. If iron reacts with oxygen, it will form iron 3 oxide, which is rust. Hydrogen and oxygen will react together in a chemical change to form water. In both cases, we have made something new that did not exist before. Here we see just a couple examples of physical or chemical changes. In a procedure called chromatography, we can separate components of a mixture from each other. In doing so, this doesn't actually change the components. It doesn't make anything new. We just separate them. Therefore, that's a physical change. In a procedure known as electrolysis, if we zap a solution with electricity, we quite often will have something new. For instance, if we have water and zap it with electricity, we can break it down into hydrogen and oxygen, which are both diatomic molecules, and so we'll have the formula H2 and O2. This is a chemical change because we've made something new. The pure hydrogen and pure oxygen did not exist before. Take a couple of minutes here and practice. Try to determine which of these are chemical and which of these are physical changes. Pause the video, determine which is which, and then restart the video for the answers. The mulching of leaves is a physical change. All we are doing is taking leaves and making them smaller. We're not changing what they actually are. They're still leaves. Milk turning sour is a result of chemical reactions that are occurring in the milk to make new compounds. The odor of mothballs is simply molecules from the mothballs, something called naphthalene, interacting with the sensors in your nose in order to detect the smell. When we melt ice, it is still H2O. It has not changed what it actually is. When beer goes flat, that's a result of all of the carbon dioxide escaping from the liquid. We have not changed what it actually is. We have just separated the carbon dioxide from the liquid. If you have any more questions about chemical or physical changes or chemical or physical properties, be sure to read your text or come see me.